Hey, this is Horner. We're going to look at 2001 M3. You have this apparatus set up where you have a pole that can turn. There's a string wrap around it. It goes to a pulley down to a mass of 4M. And then up at the top of the pole, we have 2L. So a length would just be from the center out. So that's your radius. And then we have these little masses M. So that when you let go of 4M, it goes down. And then that in turn turns these two things so that they spin. So the first thing they want us to do, really simple part here, is just determine the rotational inertia of the rod and block apparatus. So that's the top part. So we know rotational inertia is equal to the sum of mr squared. That would be equal to ml squared, since that's what we're dealing with. L is our radius here, plus ml squared since there's 2. And our final answer here would be 2ml squared. We'd end up with 2 points here, 1 for that, and then 1 for showing how you got to the 2ml squared. Didn't give you enough room to do part B, so I'm going to start it up a little bit, kind of where I left off with the other one. They want us to determine the downward acceleration of the large block. So to do that, we know first and foremost the force is equal to the mass times acceleration. That'll give you a point right off the bat. And if you remember our diagram, we have 4m is the mass that's hanging minus the tension that's going up, and that should be equal to the entire mass. So that would be 4m times the acceleration. Torque is equal to I alpha, or you can say that's equal to the tension times the radius on that pole. So I alpha here is equal to T times the radius. Tension then would be equal to I times alpha all over R. And then we'll go back and remember we said that the tension, so from up here, is also equal to 4mg minus 4ma. And if I put these two equations together, I get I alpha over R is equal to 4mg minus 4ma. So this part was for the spinning part. This part was for the part that's falling. So that's kind of what you would see. You do get 1 point for this. You got 1 point for doing this one. And then for all this, you get 1 more point. Next thing we need to do is go through and put everything into our equation. So now we've got 2ml squared alpha. So remember 2ml squared is our I. So that's our I. That goes right here. Times alpha. And we divide that by R. So now we've got this expression is equal to 4mg minus 4ma. And for doing that substitution, they give you a point. We know that alpha is equal to A over R. And so now we can say 2ml squared A over R squared. So when I plugged the A over R in for alpha, it's A over R times R. So there's my R squared is equal to 4mg minus 4ma. At this point, we can cross off M, M, and M. And to get these two A's to be 1A, we're going to have to add to the other side, find a common denominator, do all that fun stuff. But then in the end, you're going to end up with A is equal to 2gr squared over L squared plus 2r squared. So I'll let you do the algebra, a little bit more complex algebra to go from there to here, but that is your last of the 5 points for letter B. Let's go ahead and look at the next page, which is going to be letter C. It says, when the large block has descended a distance d, how does the instantaneous total kinetic energy of the 3 blocks compare to the value of 4 mgd? So this one's going to be equal to 4 times mg times that distance, because we know that ug is really equal to mgh. Here our mass is 4m times g, and then the distance it drops is going to be d. So that's kind of why that happens. Now, your explanation is the kinetic energy gained by the 2 smaller blocks comes from the decreasing potential energy due to the gravity in the 4m block. So that's what you see for part C. You get 1 point here. You get 1 point for talking about the kinetic energy gained by the two smaller blocks, and that it comes from the decreasing potential energy. That's the third point of the 4m block. So as long as you do those things, you get all three of the points. For the next part, they want to know the system is now at rest. The string is rewound around the pole, so they kind of tell you some other things. You'll need to read that. When the large block has descended at distance d, how does the instantaneous kinetic energy of the three blocks compare to that in part C? So they've changed things a little bit, and you'll notice that in this one, these blocks have kind of moved out to the side. So now they are no longer down low. We've come up a little bit, and if they come up, we know that we've gained some potential energy. So if they've gained potential energy, then they won't have as much kinetic. So we need to say that this kinetic energy is less than before. So we're going to say here that the small blocks rise and they gain potential energy due to gravity. So our total energy, ET, is equal still to 4 mgd. Therefore, the kinetic energy must be less than in part C. So you get 1 point for this, you get 1 point for this, and 1 point for this. And that is the end of this problem.